Hello.
Hey, 1 second, just setting up. Right, okay, set up. Are there any questions?
Will you be going into a little bit more depth about the email that you sent before about the final exam?
Yes, that's the first thing that I'll talk about.
Okay, awesome. Thank you.
Okay.
Sorry, can I ask another question?
Yeah, of course.
Will you be posting the solutions for homework 4 before the final exam?
Yes. And I should decide what I want to do with homework 5. I might actually want to give you fewer days to solve it so that I can post the solutions before the final for that as well.
Okay.
Although I should mention, okay, I'll get into this in a second.
I have a question.
Yep.
I know you said you're like backed up with grades and everything, which no rush. Are we gonna get like, I know you said you're gonna post the solutions for like homework 5 and stuff before the final. Are we gonna get like the grades for those assignments before the final? Like, I know you said you're kind of backed up with it, but like,
I don't think I'll get the grades for everything before the final, but I will get the grades for some of them.
Thank you.
So there is a 0% chance that I will finish all of the grading before the final. I am, however, going to change how I grade. Spending 20 minutes on an assignment is not tenable. I'm probably going to switch to a letter grading format for the remainder of the assignments. I'm still going to read everything that everyone writes, but I'm not going to make comments on it. And I'll probably make up a shorthand notation for comments, which you can decipher from a key that I give.
Okay, thank you.
Right. Any other questions? And I'm about to discuss the situation of the final. Okay, well, so the short story is that you have not seen all of the final exam submissions from my end, but if you just look over the submissions and spend several hours thinking about it, it becomes clear that a take-home exam just does not work in Calculus B. I'm pretty sure that that doesn't work. The problems are very amenable to just typing it into Wolfram Alpha and then getting an answer out. And a lot of people do that. And then it's really obvious that a lot of people do that. But even beyond that, there are lots of instances in which people did not cheat and are not going to be penalized for cheating, but they still found static resources that had very similar answers, and it's clear that they wrote answers that they did not understand. And when that happens, that just breaks the exam format. So that's not cheating, but for me, that's highly suboptimal. And at the same time, there are a bunch of people who actually clearly put a lot of work into their exam and clearly understood the material. With about, let's say, a third of the exams, it's obvious that the people are producing genuine work and that they genuinely understand the material. And the problem is that it's not the case that the remaining 2/3 are academically dishonest. For a quarter of the students, it's obvious that there's cheating. And then there's a very large zone at which I actually can't tell the difference. But statistically, people should not be doing so well on several of these problems, and there are steps that are being skipped. So how do I tell the difference? And I'm now stuck on that. And so the exam is somewhat useless as an indicator for me for the ranking that I want to produce in order to allocate grades. So oral exams are known in the business as being the clearest way to just see past BS. Oral exams are unBSable. The point of an oral exam is the examiner tries to discover what your weaknesses are. I will ask questions to see what the limits of your understanding are. Now, at the same time, I sent an email to the undergraduate's director and I asked him if I could run an oral exam. And he said yes. And he also gave me some advice on doing this. So he said that I should give you several questions to prepare ahead of the exam. Now, these aren't going to literally be the questions that I ask about. And also, there are going to be more questions on there than I'll ask about. But what you submit will be a rough basis for the questions that I will ask. And I might ask different questions of different people because you might have like 5 responses there. 5 is just a number I pulled out of my head right now. And I may see that, oh, I have some curiosities about what you wrote here. And so I might ask you about that. So some of the questions that I'll ask you are just questions to ensure that you actually understand what you wrote. The other questions that I'll ask are, well, most of the other questions that I'll ask are, I'll take the examples and I'll modify them in some way. And I'll ask, well, what would you do in this situation if instead of this, you had this? And then you don't have to do the entire problem. You just have to tell me. And then it's might be a rapid fire burst of this. But if I have a suspicion that you don't understand something, then that's a lead in for me to ask follow-up questions and discover that you don't understand something. So again, in an oral exam, the examiner is trying to show that the student does not understand a certain material that they claim they understand. So probably the best rule about oral exams is do not try to BS, because that just puts you in a bad position. Oral exams in this case are short. It's just a 20-minute exam. So your goal is to look good in the exam. Your goal is to perform in a way that looks impressive. And if you BS and then I hone in on that BS and then we realize that, oh no, in fact, you didn't know what you were talking about, then that's some time that's been spent. And then a portion of your exam time becomes you trying to explain something that you don't understand. So if you don't understand something, say right away that you don't understand it. That's good. At the same time, it's always bad to say that for every single question. You also have to do something that looks impressive. But since I'm giving you some of the questions ahead of time, or at least questions that are going to be related to what I ask, if you answer those questions and you understand what you wrote for all of those questions, then you're in a fairly good position. And I should say, so I will give you some, exam relevant questions ahead of time. And I'm going to change the rules for what you're allowed to do. It is going to be you have to solve these and submit them online. Prior to your exam. And for solving those questions, the status is it's a semi-open book for the while you're solving those questions. So the pre-exam solving is semi-open book, which is a difference from what we had on this midterm. So in specifically, you are allowed to use the lecture videos and anything on the course website. That's it. So in particular, no external resources. And this is because, well, first off, if you're getting things from outside sources and you're not fully understanding it, then that's putting you in a very bad position for the exam. remember that this written thing that you're submitting isn't going to be graded. It's going to be the basis of the questions that I ask. And if you prepare it using outside resources, there's a good chance that it is going to put you in a bad position for the oral exam. Because you have a much higher chance, this is my experience from spending several days looking at the midterm, that you will not in a genuine sense understand the solutions that you wrote, and then you're screwed. So don't do that. So you have to solve it very independently, but you're allowed to consult the lecture resources. So our internal resources, the lecture videos and what's posted on the course website, which includes solutions to the homeworks and to the midterm, right? And then I will look at this before the exam. And I'll ask you questions about it and related questions. With the goal of exposing what you don't understand. And of course, I'm not going to give these exams a numeric grade, but I'll give you a letter grade for this exam. After all of the exams have concluded, not immediately after each individual exam. And the other thing is, for me, it's really useful because for the purposes of producing a ranking of how much students understand the material, things like raw scores on the assignments, like numbers don't matter that specifically. I create a spreadsheet in which I have a bunch of numbers, and I cross-reference those numbers against what my proposed ranking is several times to sanity check that I'm not doing anything wrong. I spent quite some time thinking about this, so it's not at all washy because a lot of thought is put into it. But then having a 20-minute interaction where I get to exactly poke at students and see what they understand and don't, that's really useful to me for grading. So as far as my planned grading scheme works, this is excellent. This is what I want. And take-home exam just doesn't work. The questions that you'll be given, there's going to be a bit shorter than a take-home exam. Probably going to give you 24 hours to do them as well. I mean, the exams, the exam is going to be over 2 days. Oh, okay, I should give you more than 24 hours because that there's a strong incentive to do one day or the other. Sign up is going to be first come, first serve, but I am not going to release that tonight. Maybe tomorrow after I look into a few things. If you've been working hard in the course, and if you're one of the people who's been coming to my office hours regularly, then that's pretty good. You're in a position where you just do the preparatory questions in a genuine sense. And then once you have your answers, you know that I'm going to scrutinize your answers. So ensure that you understand what you wrote. On this exam, I know that more than the people who cheated, there's a much bigger circle than the people who cheated of people who did not understand the solutions that they wrote, although it's technically fair. And that's suboptimal. And this exam format exactly avoids this issue entirely. So that's why I'm going with it. And the undergraduate director said that I could. So word of God is that we can't complain about this. Any questions?
For the material for the final exam, will it be that of the midterm and everything else, or will it be what we learned? And I know that we've been doing a lot of the different integrals as well. Will it be from the midterm on, or will it include just to see what to
It
study?
will 100% be cumulative with probably a bit of a stronger emphasis on the earlier material. This will be cumulative. With a slight emphasis on the earlier material. And by earlier material, I mean on computing integrals. And in particular, I'm going to ask you related questions that aren't exactly the questions that appeared. And I might give you like half a calculation and I'll say, well, here we have this. What substitution would you make if I had this? On the preparatory exam, you had this situation, but if I change it to this, what substitution would you use instead? So questions of that form.
I have a quick question.
Mhm.
For the oral, like we can prepare and all that stuff, but once we get to the actual oral, I'm like you said, like before that, the pre-exam was like semi-open note. Are we allowed to have like
Yes.
notes in front of us to glance or no?
So the way that it's going to work is it is strongly advised that you do not have you do not spend time glancing at notes. You can prepare like you can prepare a very small, you can prepare a cheat sheet. A cheat sheet. Well, you should also have your solutions. So your solutions, where since we're going to look at them, that might be something that's actually you would like to potentially print out and have in front of you. That's a good point. Like plus maybe a printout of your solutions.
Okay.
If you don't have a printer, it's fine. You can look at it on your screen. But you do not have time to look at books on the exam. If you open a book and you start reading it, you're doing something wrong. It's a 20-minute exam. You don't have time for this. Your goal, it's like an Olympic performance. I want to see you do a series of impressive tricks. The more correct things that you do on the exam, the more impressive your exam looks. If you start with a question, then you say, let me open a book, and you start leafing through the book and you're wasting time, you're not doing impressive things in your exam. So that counts poorly. So that's a poor exam performance. You should not be looking at books during the oral.
Just
not
to,
be spending time. Go ahead.
just to clarify, I just want to make sure. So you're not like gonna ask us to like solve a problem on the spot, right? Just because like they take me time. Like I'm not gonna have the time to do that. Like you're just gonna ask us like questions about the work we did. It's not gonna be like you're gonna give us a problem and we're gonna have to like walk you through what we're doing.
So what I'm going to do is some of the questions are going to be exactly about the work that you submitted. The other work questions are going to be of the form, I'm going to change the problem a bit. And I'm not going to ask you to do the entire problem on the spot, but I am going to ask you to do 1 or 2 steps of the problem on the spot.
Oh, okay. All right.
But they're going to be of tricks that are related to the tricks that you've seen before. So in other words, if someone gives you perfect solutions for the preparatory problems and you understand those solutions, but you don't understand how you produce those solutions on your own, then I will also be able to detect that. So you need to understand how you would produce those solutions. It's impossible in a 20-minute exam because 20 minutes is on the extremely short end for an oral. If I had a much smaller class, I would do a longer oral, but with 24 students, 20 minutes, plus I have to spend 5 minutes like looking over your work ahead of the exam. So that's going to take me 10 hours, 5 hours on each day. But right, I'm getting off track. it's, if you look at just like a single full integral that involves a trig substitution, that would reasonably take you 20 minutes to do. And I do not want to spend the entire exam on a single problem. So I would ask you to, for example, you have some radical, you have something like radical 9 plus, I would write something like 9 plus x squared, and I ask you what substitution, so it's some compound expression, but then you have this, and then I ask you what substitution would you make? And then you would say what?
A tan of theta or x.
What is a?
3.
Yes, 3 tan u. Or theta, you could use theta instead of u, that's fine. But 3 tan u, yes. So questions of this form. Where on the preparatory thing, I would have a trig substitution, and then I would ask you, well, do you understand trig substitution? What substitution would you use in this situation? It might be a different substitution from the one that you saw exactly on the problem, but and then again, I'm not going to ask everyone exactly the same questions. If I look at your work and it's flawless, then you're going to get one set of questions. If I look at your work and I think that you don't understand one of the solutions that you've written, then you're actually a bit behind, and I'm going to start interrogating that solution. And if I actually successfully interrogate it in the sense that you actually did not understand what you wrote, then your exam is off to a very bad start. So how to prepare, most important point. Understand the solutions that you submit. So I'm not going to ask you to explain your entire solution because that takes too much time. But a good way to practice would be perhaps you imagine that you have a rubber duck, and the rubber duck is, you're explaining something to the rubber duck, and then you would explain to the rubber duck exactly how you did your solution. You should be able to explain your solution clearly from start to finish, exactly what was done at every point orally. That's a good way to prepare. Oh, I didn't finish the sentence before this. You should not be spending time looking through long printed resources during the exam.
Wait, so will we be penalized for not being concise with our answer? Because that would be wasting time.
Yeah-ish. It is best to answer as quickly as possible so that you get more tricks in, because then you get to do more impressive things. If you stall or you spend a very long time thinking, then it looks bad, because your goal is to show me that you understand an appreciable portion of the course material within the confines of a 20-minute exam. It's if you get through something, so you can, for example, if you understand something, if you definitely understand it, you can work out the optimal line that would convince me that you understand it without you giving an entire explanation. So it's possible often when you're trying to talk to someone, it's really easy to tell if they know what they're talking about. And sometimes they can say the exact correct line, and then you know for a fact that they know what they're talking about. Despite the fact that they haven't gone through all of the details. So that's what you're aiming for.
Okay, thank you.
Looking through the wrong resources, so this is wasted time. So for the top third of the class, you can consider this exam an experience, and you can go into it expecting it to be fun. Like you might get caught on something that you don't understand. That's fine. My goal is to find poke holes in your understanding. So it's not the end of the world if I poke holes in your understanding, but you should remember how the exam is going to be used. the exam is going to be used and that I want to produce a ranking of all of the students. And then after I produce a ranking, I'll set grade boundaries via an understanding of exactly how people place in that ranking and via natural performance gaps in order to insert the grade boundaries so that small differences in performance wouldn't ever push you past a grade boundary. There are always gaps. And then you're like, okay, it's pretty obvious this is a good place for a grade boundary. And so the goal is to do enough impressive things and to look good on the exam. There's an art to doing oral exams in that sense. And it's not the end of the world if it goes wrong. It's also very susceptible to chance. Oral exams are much less consistently performable on than written exams. And there's just a chance that I might ask you exactly the question that you'd dread hearing. So that sometimes happens. But once again, numbers don't exactly matter. And you should believe that I should be able to accurately gauge your mathematical ability. And that contributes to the ranking. In some sense, then, it's not just about doing the work, it's also about understanding the material. So submitting full solutions to previous things isn't a substitute for understanding the material as well. You had to have done them genuinely and you had to have gained some understanding from it. And if that's missing and the exam exposes that, well, then you're accurately getting placed in the ranking. But then again, remember, half of the class is going to be getting, well, definitely in the A or A minus range, at least half of the class. At the bare minimum, half of the class is getting an A or an A minus. So if you look, I sent a previous email about my grading scheme. I showed you Scott's grading distribution. I'm going to give you a better grading distribution than that. And I'm only going to give people C's if I actually have sore objections to the work that they put in this class. Not having submitted a large number of assignments looks very bad. So if you have missing assignments, that's not a good sign. If you can magically still learn all of the material and do well on the oral, well, okay, you can rescue yourself from that. You can dig yourself out of the situation. But if it looks like you don't understand the material on the oral and you haven't submitted the work, well, okay. Now you're in the C range. So if you have, or if your submissions are just very bare bones, anyway, you get the general sense. I spend a lot of time on this, and so I think I produce a fair ranking. You just really get a sense of what people understand after looking at it very carefully. That's the main gestalt of the ranking, well, of the grading system. Any other questions?
Yeah, I was trying to look for a date for the final exam. So is it going to be towards the back end of the week or the front end of the week?
Well, it looks going to can anyone tell me when the summer semester officially ends?
I think it's July 1st.
And what
Which is
days of the
Thursday.
week is that? That's Thursday.
Yeah.
Okay, I'm probably going to do the exam on Wednesday and Thursday then, because I can't do it on Friday.
Okay.
So I can probably, I am allowed to do the exam on Thursday, right? It's still, okay, Canada Day, by the way. So the exam will be on Wednesday and Thursday, and then I will probably make the assignment due at so homework 5, I'll say is due. I'll make it a shorter assignment to compromise. Due noon on Wednesday.
So is homework 5 the problems that we'll be using for the exam?
No, homework 5 is going to be problems on polar coordinates and improper integrals, which is what I'm going to discuss today.
So we should
and
have
this is going to
homework
be a
5
shorter
and
assignment.
the questions done.
Yes, but I'm going to make homework 5 shorter, and I'm only going to give you the questions with no, I'm not going to give them to you before the end of the weekend. So the idea is that you work on homework 5 until like Monday, and then you switch over to this, but you should also prioritize the preparatory problems. So you should not prioritize homework 5 over those preparatory problems, but there are going to be several days in which you can work on homework 5. So I'll make this shorter.
I just have
And
another
then-
quick, oh, sorry,
yeah.
go ahead. A quick question regarding the grading. So say like we understood the first half before the midterm better than the material that we're learning now. Is that something that will hurt us? Or if we show that we're putting effort in to learn this material, like are we going to be graded based on effort at all for the oral presentation? Or is it strictly based off of the problems that we produce?
I am happy if you understood something. That means that if you understood the first half of the course, but not the second half of the course, I'm fine with that situation. And then you can just tell me directly in a no BS way that I don't understand these topics. Please don't ask me questions about them. And then I'll just take note of that. And then you're otherwise using the time effectively, right? Plus, I sort of am not personally fond of applications questions as much as I am fond of the earlier material. I think that the core of the course is what we did at the beginning. And so if you understood the first half of the course, then actually that's better for you then. Well, you can't counterfactually understand the second half of the course, but not the first half of the course. And as for whether effort goes into it, well, if you put in effort onto your assignments, then I'll be able to tell that, right? It's not just the final exam. I'll be looking at that as well. It also will statistically leads to a better oral performance. I mean, if I get that, go ahead.
Is the exam next week, Wednesday?
And Thursday. Yes, and then I'll release signups. You know what? I'll release signups tomorrow.
I asked if the exam is next week, Wednesday and Thursday, or is it the following week?
Next week.
And one more question. So the pre-exam, like the written portion, you'll be releasing that before Wednesday, Thursday?
Yeah, let's see.
Like,
I
don't know.
I will decide whether I'm going to release it on Monday or Tuesday in a bit.
Okay, thanks.
I'll tell you.
Thank you.
The reason, so here's the counter argument for releasing it on Tuesday. That's that it incentivizes people to sign up on one day in front of the other, and then people will feel resentful that they didn't get a slot on Wednesday. Sorry, that they didn't get a slot on Thursday and that they had to sign up for Wednesday. So that provides a better argument for releasing it on Monday, but then I feel that you're having too much. So it goes both ways. Maybe Monday, Monday or Tuesday. So I will release signups tomorrow. And this is first come, first serve. If you're signing up late and you absolutely can't make the time, then you can tell me and we can make an arrangement, but you better have a good excuse. So if all of the Thursday slots are taken, but so if you can hypothetically make a Wednesday slot, then tough luck. You're taking that Wednesday slot. If you are literally at work the entire time and you can't get out, then okay, fine. I don't want irregular time slots, too many of them. First come, first serve. And again, if you're in the top half of the class, this exam format should work in your favor. Yeah, and then again, it's stochastic, so it might not be perfect. It's never perfect. I guess I'll also look at your work ahead of time. I'll have some notes. I mean, just apart from the 5 minutes before the exam. So there are going to be 20-minute time slots. You have to be on time. Okay, like be on time for your exam. Because you're going to throw off my schedule otherwise. And I'm not going to put in more five. Be punctual. If you're 3 minutes late, then your exam is 3 minutes shorter and you have less time to do impressive things. So I will slot them as 20-minute slots of 5-minute gaps. Which means that throwing off my schedule would be very bad. I will not have my schedule thrown off. If you completely miss your exam, well, I'll be pretty frustrated, but we can sort of make up for the end of the day, but it's going to count against you. Showing up 5 minutes late is bad. That just counts against you in a very direct way. And I reiterate that the main purpose of an oral exam is that it is the most efficient way to have an exam format that is unbiasable. Oh, and there's a chat question. Let's see. Okay. Rewatch I'll post the recording to this. So the question is basically re-explain everything that you just said. You should watch the recording. Is that okay? I'll send that out as soon as it gets there. I can answer questions that are more pointed than re-explain everything. And once again, the reason what I started by saying is that the reason that I'm doing an oral exam is because I really have no other choice. I explained how, as an indicator of student performance, the midterm was fairly useless. There's a very large gray zone in which I just have absolutely no idea whether or not people produce genuine answers. Like I have a group of submissions and maybe half of them are genuine, which means an arbitrary submission has a 50% chance of being genuine. I'm not just accusing those people of cheating, but I know that statistically it looks like, and then that's just useless to me as an indicator. And then it's unfair to the people who worked hard, right? So we have to do a format that's unbiasable. It's taking me at least 20 minutes to grade a paper anyway. So this way, I'm going to spend as much time as I would grading a regular written exam. And if I had like a proctored exam, well, first off, that's not fun. And second off, I'd still be spending 20 minutes grading each paper. So because grading takes me way too long, I may as well, instead of spending the time grading, which I'll just do for my general impression of the exam, I can spend that time talking to students. And it's much more useful for the way that I'm going to grade. Right. Well, okay, now I think we've covered everything. And then if you joined late, look at the recording. So I'm going to move on to the material, although I'll take any last questions if there are any.
Are we still doing a review session on Thursday?
Yes, I'm
Okay.
planning on finishing the material today. Thursday is going to be a review session.
Awesome. Thank you.
So I felt that I needed to pad out today's lecture. If I padded it out too long and I go over time, then I will spend part of Thursday doing new material. Although my current plan is to finish all of the material today, have like half an hour left for some extra stuff, and then just do a review on Thursday. Okay, so getting into the material. Calculus time. How much time did that spend? Not bad, only 10 minutes. Really? That felt longer than 10 minutes, calculus time. No, we started at 30 minutes. That was only 10 minutes. So last time we were in the middle of discussing polar coordinates. And what are polar coordinates? So you have coordinates r and theta. Then if you have your plane, for example, all angles are measured against the positive x-axis. And in math, the positive direction is counterclockwise. So for example, you would measure a ray right here. Let's say this is the 45-degree line. So this angle would be pi over 4. Then if it were the minus 45-degree line, the angle would be minus pi over 4. But also angles are defined up to additive multiples of 2 pi. Well, additive summands of 2 pi. So pi over 4 is the same angle as, 2 pi plus pi over 4, which I can, 4 times 2 is 8, 9 pi over 4. It's the same angle as pi over 4. Then, so that's how angles are measured. And then r is measured as units of distance across one of these rays. So then I could take, for example, a point here. And then I could perhaps find that this distance was 2. And then that point would be the point 2 comma pi over 4 in polar coordinates. And what we were getting to is ways for converting equations in polar form to Cartesian form and vice versa. So remember that we had that if we had Cartesian coordinates, x comma y, then r we could write as the square root of x squared plus y squared. And cos theta, what would the expression for cos theta be? So imagine that you have a point with coordinates x comma y. This is the point 0 comma 0. This side length is x, this side length is y. So what is cosine of this angle?
Is it pi over 4?
In terms of x and y.
Oh, my bad, my bad. Is it 2?
Just the number 2 in terms of x and y. No, not for pi over 4. I mean of the point x comma y. R is equal to the square root of x squared plus y squared. Cos theta is
X.
So x is this side of the triangle, but what's the hypotenuse?
X over 2.
X over R.
Yes, x over r. So x divided by the square root of x squared plus y squared. Why? Because if in this triangle we have this side as x, then that side is y, then the hypotenuse is x squared plus y squared. And so cosine of this angle is this. And similarly, sine of theta is y over square root of x squared plus y squared. Then we saw last time that if we actually wanted to find out what theta was, then the formulas were defined case-wise by cases, and it's not so elegant. So it's much more elegant to say what cos theta and sine theta are. I can also say what tan theta is. What is tan theta?
x over x squared plus y squared over y over x squared plus y squared.
Sure, but what does that, when you cancel those, what do you get?
Just sine over cosine.
Right, but these have a common factor. So after you cancel that common factor, what do you get?
Y over x.
Exactly. And then if you look at this triangle as well, you can see that these two signs are y and x, so you can divide them. And of course, this isn't defined when x is equal to 0, but then you're on this line, and indeed tangent isn't defined on that line. These expressions are defined everywhere except for the origin. At the origin, they don't make sense because we don't have an angle that works. So last time we were discussing how to convert from Cartesian to polar. Oh, I should, okay, I should mention the other thing. If you have r and theta, then what are x and y in terms of r and theta?
R cosine theta and R sine theta.
Good, exactly. And why is that? That's because we can draw the triangle. This is theta. This is r. Then, well, cosine theta is the ratio of these two sides. And then if you rearrange that, then you get that this side is r sine theta. Sorry, I meant to say sine theta is the ratio of these sides, and this side is r cos theta. So also direct trig. Okay, now Cartesian equations to polar equations. So we did one example of this last class, and let's do a second example. So up to now has been review of what was covered last class. Let's consider just the parabola, y equals x squared. So if I want to convert this into polar coordinates, I can use these formulas for what x and y are in terms of r and theta, right? So that tells me that r sine theta is equal to what?
R cosine theta squared.
Sure, r squared cos squared theta. Now, assuming that r isn't 0, I can divide through by r. So this is only works when r does not equal to 0. And then I get that r is equal to, what do I get overall? I get sine theta, that what else do I have to write?
Over cosine squared theta.
Yep. And what's the nicest way to write that in terms of other trig functions?
Tangent times secant.
Exactly. And so notice that this expression fails at theta is equal to pi over 2. So there's no point on this ray. So this is defined for, let's say, 0 is less than or equal to theta is less than or equal to pi, except at pi over 2. So if we look at what this graph looks like in polar coordinates, it will look like the parabola less the point at the origin. Because of this step where we divided through, this is what the graph looks like. Well, if we just plot this equation. If on the other hand, we plot this equation right here, then we get the full parabola. This step, we sort of, it's an uninvertible step, so that this equation holds Yeah, this step can't be done if r is equal to 0, which is what happens when theta is pi over 2.
Can you explain that graph one more time?
Sure. So tan of pi over 2 fails, right? And if we look at sort of all of the rays, sorry, I made a mistake. For 0 less than pi, like this, because yeah. Wait a second. So if it's sine over cosine. Hum. Yeah. Well, this is the graph of y equals x squared. I'll say this. Now we have a graph in polar coordinates. So these graphs should be the same modulo points at which this equation fails. Cosine is 0 at pi over 2, so this equation will fail at pi over 2. And if we imagine all of the other rays emanating from 0, we get a point on this graph. So all of these points exist. This point would be accounted for by the pi over 2 ray. And I admit right now that I have some reservations about this explanation. So that's the best explanation that I'll give for this graph. Is that okay?
Yeah, and then just backing up to where we have sine over cosine squared theta.
Yeah.
How do we directly get that? Like, what was the step that you did?
So I crossed out a power of r from both sides. And then I have sine theta is equal to r cosine squared theta. And then I divided both sides by cosine squared theta. Does that make sense now?
Yeah, thank you.
Okay. Now, I have a specific reservation about this example, so let's just not delve into it further, because it's going to occur to me after the lecture how that reservation is fixed. I'll think about it later. But for now, the math checks out. X is r cos theta. So yes, this is what we get. Now, let's look at the following equation. Let's imagine that alpha is some number. Alpha is some fixed number. Consider the equation x cos alpha plus y sine alpha.
This is a separate problem, like a separate
It is.
example, right? Okay.
Yeah. Equals to p for some other value. And then if we look at what the graph of this looks like, you could consider the angle alpha. Let's say that this line right here is at angle alpha. And then you can go p units across that line. So let's say this is a distance of p. And then what you're parameterizing is the line that's perpendicular to the ray at angle alpha. Distance whose closest points to the origin is distance p. So this is the graph of this equation in terms of p and alpha. And then in classes like Calculus 3, you'll be doing this in 3 dimensions, and you'll be very used to why this equation holds. But if you just think about it, you can see that this is the graph that you get from an equation of this form. Now, the question is, okay, let's convert it to polar coordinates. So x becomes what?
R cosine.
Yep. So r cos theta and then cos alpha. And y becomes?
R sine.
Mhm. Good. And how can you rewrite this expression? We can write it as r times what? Looking at this expression, cos theta times cos alpha plus sine theta times sine alpha.
Can you write cosine theta plus alpha plus
So
or
there's the thing, cosine of, let's say alpha plus beta is equal to cos alpha, cos beta minus sine alpha, sine beta.
okay.
So what should it be? You're correct that you're using this formula, but how do I change the sign here? Sorry, cos alpha, sine. What can I do instead of adding alpha?
Subtract it.
Yeah, if we look at what happens, cosine is an even function. So cosine of minus alpha is the same as cosine alpha, whereas sine changes by a sign. So if you consider a cosine alpha minus beta, then it exactly changes to the plus sign. And so, or we can write, if we really want to, r equals p secant theta minus alpha. If we want to write, because typically we write polar equations of the form r equals f of theta, right? And that's why I'd like to rearrange it as r equals something. That specifies what the radius is at a given angle. And then if you look at what the radius is at a given angle, it's secant theta minus alpha. Okay, so those are the three examples. We did one yesterday of going from Cartesian coordinates to polar coordinates. Let's go in the reverse direction.
Professor?
Yep.
Just sorry, quick question. It's the secant because it's the 1 over, because you're dividing by cosine?
Exactly. 1 over
Okay.
cos to secant, right? And the reason that I'm dividing through is because we often want to write r equals f of theta. That's the standard form. This is like the y equals f of x analog. So this is the polar analog. And it's sort of easy to plot it because you just ask yourself, what is my radius at a given angle? And then you go around the circle and then you plot your radii. And then you can, in the way that you plot several dots in high school and then connect them with a line, you'd also plot several dots and then connect them with a curve.
I guess, are we going to review some of that graphing? Because I guess I'm confused about that a little bit.
A bit. The graphing is going to be sort of secondary, but for the next few examples, I'll draw graphs as well. Now notice this is going to be an example. Let's consider r equals 2a cosine theta. Right. Okay. Now, if I have an equation like this, what I can do is r becomes what? If I want to rewrite it in terms of Cartesian coordinates.
Is it two 2x or 2ax?
Here are the equations, right? So r is the length of the hypotenuse of this triangle, right? And then cosine and sine are the ratios of the sides to the hypotenuse. So then going back to this equation, I can write the square root of x squared plus y squared is equal to 2a. And then cosine is what divided by this? X or y, which side?
X.
Because that's the side adjacent to the angle when we draw it. Now, okay, when we're doing this, our single rearrangement begs to be made. We multiply through, we get x squared plus y squared is equal to 2ax, right? Now, another rearrangement begs to be made, and I get x squared minus 2ax plus y squared is equal to 0. Now, what can I do with this expression to make it nicer?
Can you factor out the x?
That doesn't, I can do something that's much more insightful than factor out the x. I could, but what else can I do with just these two terms?
Complete the square?
Yep. So if I complete the square, I would get x. What? So let's look at what the coefficient here. It's minus 2a, right? So what goes here?
Minus a.
Yep. Why? Because if we have x plus b squared, that's equal to x squared plus 2b plus 2bx plus b squared, right? So if we have a coefficient of something, that's equal to twice the coefficient that we put here. We had minus 2a here, so we put a here, right? Now, if I wrote this equals 0, that would be false, right? Because I changed this term, I added this constant term. So what do I have to subtract to make this equation true?
Minus y squared?
Not y squared. What have I added in order to make this equation true?
Is the x?
Well, okay, if I multiply this out, if I expand the x minus a squared,
Is it a
then
one?
how is it different from the line above?
I have to add 2.
Well, x minus a squared is x squared minus 2ax plus 1.
So plus 1.
A squared.
Yeah, plus a squared. And so there's an a squared term right here that wasn't here before. So how do I correct that?
Subtract it.
Yeah. And now if I rearrange this again, I get x minus a squared plus y squared is equal to a squared. And this is the formula of a circle of radius a centered at x comma 0. So if I actually look at that, I can sort of look at the point A, and then I can get a circle of radius a. So from polar coordinates, it's not at all obvious that this is what you're getting. But when you write it in Cartesian coordinates and you complete the square, you can see that it's a circle of radius a centered at the point a comma 0. And then radius a. Does everyone see that?
So from completing the square, Where in the completing the square does it say, like, do we determine a comma 0?
Oh, so we that what we've discovered is this equation, right?
Mm-hmm.
And what is this equation? The equation of the form x squared plus y squared is equal to a squared is the equation of a circle, right?
Right.
Now, what have I done? I've replaced x with x minus a. So this translates the graph a units to the right.
Oh, okay.
So if we took all of these values and then we subtracted, we moved them a units to the left, we subtracted a from them, their x values, then you'd exactly get the equation of a circle centered at the origin.
Oh, okay, got it. So the difference is really just it got translated over.
Yep.
Okay.
And it got translated over to the exact same amount of units as the radius. So it turns out that this simple polar equation right here, it describes the circle of this form. Whereas if you had the equation, remember, r equals 1, then what would you just get? If the radius is always 1, what do you get?
It's like the spiral thing, like
The radius is constant. At every angle, you have a radius of 1. So what do you get?
a circle.
Yeah, of radius 1. So the radius is constant, right? In polar coordinates, saying that the radius is constant says that you have a circle. So the equation r equals 1 gives this. The equation r equals 2a cos theta gives this. Okay, let's do another example.
So that was going from polar to Cartesian.
This is, yeah, polar to Cartesian. We started off with a polar equation
Right.
and we got to a Cartesian equation. And before we were doing the reverse. Before we started off with a Cartesian equation and we got a polar equation. Okay, let's consider the equation r equals 4 over 3 plus cos theta. So, okay, if we just do the same thing, that tells us that the square root of x squared plus y squared is equal to 4 divided by 3 plus 1.
X
Just x?
over the square root of x squared
Yep.
plus y squared.
Now, what I'm going to do is I am going to multiply I'm going to take the bottom and I'm going to bring it over to the other side. So what I obtain is that 3 times the square root of x squared plus y squared plus x is equal to 4. I've taken the denominator and I've brought it over to the other side. And then this cancels with that, and then this becomes that. Now I am going to, am I just going to do the obvious thing?
Wait, quick question.
Yep.
So it cancels, but it's still there. Wait. Like,
Well, let's see. So I get that 3 times x plus the square root of x squared plus y squared times the square root of x squared plus y squared is equal to 4, right? And now if I multiply that out, it cancels with this denominator and then this stays here. I mean, these are 2 different additive terms, right? You distribute it.
oh, right, yeah, okay.
Okay, how do I, how do I get rid of the square root? What do I do?
You square both sides of the equation.
The problem is if I square both sides of the equation right now, I get cross terms that have square root of x squared plus y squared. So what do I do before then?
Could you multiply by the conjugate? Or
That
no?
gives me a denominator which has
Okay.
a square root. So that doesn't really help me.
Could you just like subtract x, divide by 3, and then get the square?
Yes.
Okay.
Well, I don't have to divide by 3. Let's just leave the 3 as it stands. So if I have this, then what do I do? Now what do I do? Now what do I do with this equation if I want to get rid of the square root?
You square it.
Yep. So I get 9 times x squared plus y squared is equal to 16. Then 4 times 2 is 8 minus 8x plus x squared. And then if I rearrange that, I get 8x squared, right? Plus 8x plus 9y squared is equal to 16, right? Now, if I want to make this nicer, what should I do?
Can you factor the first two terms?
Well, I could take out a common factor of 8, and then I have x squared plus x, and then what do I want to do with x squared plus x?
Complete the square.
Yep, so I should write x what? Squared plus what?
Is it 1/2 x?
Not a 1/2 x, just 1/2, right?
Oh, okay, yeah.
Now this equation right now is false. What do I need to do to make this equation true?
Subtract 1/4.
Exactly, because the linear term is correct by design, but I also have a constant term, and the constant term is 1/4. So right now this equation is false, so I have to subtract 1/4. So I can write this as 8 times x squared plus 1/2. Sorry, x plus 1/2. And then I have minus 1/4 times 8. So that's minus 2 plus 9y squared is equal to 16. And so overall, I get that 8x plus 1/2 squared plus 9y squared is equal to 18. And this is the equation of an ellipse centered at, well, the point at x equals negative 1/2, comma 0, right? And if I just look at it, if I look at x squared equals 18, well, so I can draw the picture. So it's going to have two axes. You are not required to draw this. Well, okay, let's just look at the numbers. Sorry, 8x squared is equal to 18, and 9y squared, or let's say xa squared equals 18. And 9y squared is equal to 18. So this equation gives me y squared is equal to 2. So y equals √2. I'm going to take the positive square root, and then a is equal to the square root of 18 divided by 8. which 18 is a bit smaller than 19, so it's going to be a bit less than root 2. Root 2 is about 1.4, 1.41, and then this is going to be a bit smaller. I don't know, 1.3. So if this is the 0.1/2, then we can look at the y-axis. So it has radius root 2. And then here we have the slightly smaller radius there. It almost looks like a circle, but this radius is just a bit shorter than this one. And that's my best attempt to draw an ellipse. But again, the Cartesian coordinates are more informative. If you just started with this equation, do you know it? Why would you guess that it looks like an ellipse? But if you put it in this form, then it's sometimes easier to graph. By the way, let me just tell you, I have another remark to make about the previous equation that we did. This equation, r equals 2a cos theta. If you look at a circle and you take the diameter and you take any point along the circle and you plot these two rays, then what is this angle going to be?
Are they going to be like 45, 45, 90?
No, well, it's not necessarily going to be 45, 45, 90, but the 90 is always going to be the case. So if you actually look at it and you look at a circle and you look at its diameter, and you look at any sort of angle that you can get, or let's draw it like this, or like this, or like this. Well, okay, it's it should be convex. All of these angles are always 90. So if you imagine moving this point around, you're still going to get 90 degrees. In general, if you have any chord and you move a point around, the angle stays fixed. So let's just actually interpret this. If this radius is 2a, then what is this side equal to? If this side is 2a, then what is this side equal to? If this angle is theta. If it's a right triangle, and this is the adjacent side, and the hypotenuse is 2a. Well, it's going to be 2a cos theta, right? The hypotenuse times the cosine of the angle. So this result about right angles is why this equation is the equation of a circle. You can see it this way. If you draw this circle and you draw those lines, that indeed at angle theta, the radius is always 2a cos theta, confirming this. Oh, by the way, does anyone have any questions about the second example that we did? It's somewhat similar to the first one. Don't worry about how I got the circle of an ellipse and why I knew that these were the axes. That's just how the equations of this form work. Do I have one more equation to do, or are we finally going to move on to the calculus of polar coordinates? I think we're moving on to calculus.
Can I just ask a quick question about this
Go ahead.
one, please? So what exactly is like the final answer for this one?
Well, the equation here, the question asked, I didn't write out the question, but write the equation of this in Cartesian coordinates. And then the final answer would be this equation right here. This is the best way to write this equation in Cartesian coordinates.
Okay, thank you. So we wouldn't have to necessarily write the graph with the 8a squared equals 18, all of that stuff?
Yeah, I'm not going to ask you to do this on the assignment.
Okay, I just wanted to clarify. Thank you.
Yeah. Now, let's do area in polar coordinates. And remember how at the beginning of last class, we did all of these engineering arguments? Sorry, not engineering, physicist arguments. Engineers don't argue, they just apply formulas. Physicists have physicist arguments. So we're going to do a physicist argument for defining what the formula is. Hand waving. Physicist arguments. So suppose that we have here the graph of some polar function. And then suppose that we care about this range of theta values. Anyway, so R equals f of theta for theta ranging between A and B. Now, what we're going to do is we're going to partition theta into pieces. So we're going to have some partition theta A equals theta naught less than theta 1. Or let's actually call these not theta. Let's use the notation that we were doing before. Okay, yeah, no, theta naughts. And now what we're going to do, let's say that this is the range in question from here to here, is we are going to choose a point inside every interval. So let's say that the point, you know what, I don't like, I'll make them t's. I'll make them t's to conform with the notation that we had last time. T naught less than T1 is less than Tn. And then between Ti and Ti plus 1, what we're going to do is we are going to choose S sub I. And then at each, so let's say that these are our angles. These are our points T naught, T1, T2. Then we're going to take as a reference angle the chosen angles between them. And what's the most natural thing that we could do to approximate this area? Like before we used rectangles, right? Go ahead. So
You would add all the sum of all the areas together.
But
areas of
what?
slices of the slices.
What does a slice mean? So before we used rectangles, right? If we had a function, we used rectangles. Instead of rectangles, what do we do?
Triangles.
Okay, triangles is one thing that we could do. But what's more elegant in polar coordinates?
Like angles? Like,
Well, it's not exactly a triangle, it's how would you describe it?
Lines.
Okay, I'm looking for the word circular wedges, right? So the difference between a wedge and a triangle is that a wedge has this rounded side. So, okay, let's look at this. We're going to take this point, and then we're going to take this as a radius, and then we're going to produce a wedge here. Take this point as a radius, and we're going to produce a wedge here. Take this point as a radius, and we're going to produce a wedge here. And then, well, okay, there should be some other loop point here. And then we're going to take this as radius and produce a wedge here. And so if I connect all of those lines, I get, or maybe I should have drawn those in red. A bunch of wedges like this. And the idea is that this collection of wedges, it's going to approximate the area. Now, if I have delta theta I equals to t sub I plus 1 minus t sub I. So that's the difference between two angles. And then I have my function r equals f of theta. And so I have some value f of s sub I. Then delta a sub I is going to be the area of the if wedge. How would I write the area of the if wedge? So the angle here is delta theta I. And the radius is f of s sub I, right? How do I get an area then for that wedge?
Wait, what part is the f of s sub I? Is that the?
It's the radius
Okay.
of the wedge. And the angle is f of delta I. Sorry, delta f of I. Sorry, delta theta I, delta theta I. Well, first off, what happens if we complete this to a full circle? What's the area of the full circle?
Pi r squared.
What's r?
The pi f of s sub I squared.
Pi f of s sub I squared. F squared s sub I. And what fraction of the circle am I using?
Change of theta I.
Well, how many, so that's a measure in radians. How many radians are there in a circle?
2.
No,
No.
2.
Pi, 2 pi.
2 pi. So for example, if delta theta I were 2 pi, then we'd have the whole circle, right? Does that make sense? So this is the ratio of the circle that we use. And so then the area is going to be pi of f squared s sub I times delta theta I divided by 2 pi, which is equal to, the pi's cancel out, 1/2 f squared s sub I delta theta I. And so if I write what the area is approximately, it's going to be the sum from I is equal to 0 to n minus 1 of 1/2 f of s sub I, f squared of s sub I, delta theta I. And then a physicist looks at this formula and then they say that the actual area is the integral from a to b of what? So what does the delta theta I become in the integral?
Is that the dx or?
D theta in our case. And so what does this expression become?
One half f of f squared x.
Well, what's the
Or
variable
theta.
integration? Yeah, there we are. So we have done a physicist arguments, and we have derived the area formula in polar coordinates. So this is the area formula.
And just going back up like 2 steps, when you
Yep.
like the change of a of I, how'd you get it equals 1/2 f squared s of I, change of theta?
So what did we have? If we have a wedge, right? The change of area is supposed to be the area of this wedge. The wedge has a radius of f of s sub I, and it has an angle of delta theta I. Now, what proportion of the circle does the wedge occupy? Well, if delta theta I were 2 pi, then it would be the whole circle, right?
Oh, yeah. So I had like a number written wrong, so I got it now.
Right. And so that's the product of the ratio with the area of the circle, and the pi's cancel. And so I get this. And remember how at the beginning of last class, I said that we would derive 2 formulas that were not at all obvious from first inspection. One of them was the formula for arc length, right? The formula for arc length was the square root of 1 plus f prime squared. Why would you think that that formula is the formula? Well, similarly for polar coordinates, why would you think that the area formula takes this form? And so we do an argument in the physicist argument of this form where we approximate it by slices. The integral was originally defined by approximating with rectangles. Here we're approximating by wedges. When the partition gets finer and finer, it approximates this curve much more closely.
So this is the area of one circular wedge.
What is the area of one circular edge? That's given by delta a sub I,
Okay.
right?
Mhm.
If we have a specific, go ahead.
I'll continue.
I think someone else was going to. Someone was going to ask? No? Okay. Right. So going back to this explanation again, we have the delta theta I. So we've taken this a specific approximation. We've taken a specific radius by sampling f at a specific value, and then we have a specific range of angles that we consider. And so we have this angle and we have this radius, and then we get this formula for the area of the wedge. And then we sum the areas of the wedges, and that gives us an approximate area. And when the partition becomes finer and finer, the delta theta I becomes a d theta.
Yeah,
Any
I
other
guess
questions?
I guess like what I was wondering is like, so I know we went over some other examples where you would derive a formula for a certain like shape or graph, and it would have its own derived formula. So would this be used in a special case, I guess, is what I'm trying to ask?
Well, whenever we have polar coordinates and we want to find an area, you pull out this formula.
Okay.
So let's look at what we did last time very quickly. This is last lecture. And we said, well, for example, we started off with just introducing this method in the 2 cases that we had before. Well, this case was if we had the difference of 2 functions, right? So this is sort of justifying Cavalieri's theorem for that it's this integral. Okay, well, that's a really obvious example. The less obvious example is this example about justifying the cylindrical shell method. Why can you integrate the areas and get the right answer? And it turns out that you actually have to do some work. You actually have to factor this in a clever way. and then do a bit of work, and then you actually get the formula. So establishing it in the physicist argument requires a bit of manipulation. But the formula still isn't surprising. It's just the integral of the areas of the cylindrical shells. What's more surprising is when you get the formula for arc length. There, you do a polygonal approximation of the curve, and then this term right here becomes the derivative. That's surprising. And a physicist argument shows it to you. So that was the first non-obvious formula. And then today we've derived a second non-obvious formula. Which is a formula for area. And arguments like this are particularly good to show to Calculus B students. So everyone who takes Calculus B sees this argument. And then, of course, we can do some examples of computing areas, right? Any questions before then? Does that answer your question, by the way?
Yes, thank you.
Okay, great. So here, let's do the area of the spiral. So suppose we consider R equals, let's say, a theta. And if I were to graph this, sometimes drawing graphs is actually useful. So for example, well, okay, we'll see. But this is just the spiral. We can, for example, put, and then the range of angles, I should say with the range of angles for 0 is less than or equal to theta is less than or equal to 2 pi. So we're going to go once around the spiral. Then I can consider this point right here, 2 pi a. Then sort of half of that is this, a quarter of that, half of that in turn is this, and then that plus that is sort of here. That is not half. Okay, that might be better. Still doesn't look like half. Okay, yeah. Anyway, ignore those ticks. Those were just reference marks for drawing. Okay, so what we have, that's still a pretty bad drawing, is this area. We want to find this area. And so how do we do that? Well, we have the equation, right? And then we have the area formula. So we're going to take A equals the integral. What's the range of angles that we're considering? What's the range of angles in this problem? It's stated right here.
From 0 to 2 pi.
Yep. And then I set up the formula. So I have to remember the factor of 1/2, and then I have r squared. So a squared, theta squared, d theta. And what that gives me is what? What is the what's the antiderivative of half a squared theta squared? It's a polynomial, easy integral. We all know how to do this. Are people confused because we're integrating with respect to theta? Is that the source of confusion?
Is
If
it,
it were-
is it gonna be like 1/6?
Yep,
A squared theta to the third?
exactly. That's just the variable of integration. So this is just a prefactor times the variable of integration squared. So we use power rule. And then we evaluate this from 0 to 2 pi. The 0 goes to 0. And then otherwise we get 1/6 of a squared times 8 pi cubed. And that's equal to, well, the 2 crosses out. So 4/3 a squared pi cubed. And that is the area of the spiral. Nice that pi cubed appears. So that's pretty cool. Now let's consider, so this is example 1. Graphing it wasn't necessary. But I will graph it just for the sake of reference. Let's consider the equation r equals 2 plus cos theta. Now, how would I graph this? Well, the radius ranges from what's the smallest this gets and what's the biggest this gets. When is cos theta, what is the smallest value that cos theta attains?
Would be -1.
Yeah, so the smallest value of this expression is 1, right? And what's the biggest value that this expression ever attains?
Would it just
It would be,
or no?
what would it be?
I said 1, but
Well, that's of cos theta. And so the expression itself has maximum value, this entire expression.
3?
Yeah. So what I'm going to do to graph this is I'm going to draw these 3 concentric circles of radius 1, 2, and 3. So when theta is equal to 0, cosine theta is equal to 1, right? So I know that I have a point here. When theta is equal to pi, I have a point here. It's -1. And when theta is equal to pi over 2, it's cosine theta is equal to 0, right? So I have these points right here. And then let's say that I want to do this integral for 0 is less than or equal to theta is less than or equal to 2 pi. And if I'm graphing that, well, cosine, it becomes 1/2 at an angle of 60 degrees. So if it's 1 here, then it's 1/2. So it's halfway here at this angle about. Okay, and then if I, well, okay, and let's see. Well, like, that's. Okay, and then if I draw this. I get something that looks like this. It's not exactly a circle because it bulges out at this point. And so I get this weird shape, but it has a bulge here. So it sort of bulges here. Not exactly a circle, but it's some sort of circular-ish shape. And so what I want is the area of this region, of course. So setting up the integral, I get the area is the integral from 0 to 2 pi, specified angles. And then what do I write? What's the first thing that I write in this formula?
1/2.
Yep. And then what do I write next?
The function squared.
Exactly. Right, and then if I just expand that out, well, okay, I will write it out like this, 4 plus 2 cos theta. Sorry, plus 4 cos theta. Because it's twice the product of these, plus cosine squared theta. D theta. So that's integral from 0 to 2 pi of 2 plus 2 cos theta plus 1/4 plus 1/4 cosine 2 theta.
Where'd the 1/4 come from?
What formula am I using when I'm integrating cosine squared?
Oh, the half angle in the.
Yes,
Okay.
cosine squared theta is equal to 1/2 1 plus cos 2 theta. And then I also have this 1/2 out front here. Right? So that gives me that. And then I can just directly write down the antiderivative. So that's 2 theta. What's the antiderivative of cosine?
Sine.
2.
Yeah. Then, well, I guess this 1/4, really, this became, I should probably just combine these. This became 9 quarters, right? Two plus 1/4. And then I can do this antiderivative in my head. If I differentiate sine 2 theta, I get 2 cosine 2 theta. So I should divide by 1/2. And then I evaluate this between 0 and 2 pi. So if I look at it, sine is always 0 so if we look at the graph of sine, it's 0 here, it's 0 at pi, it's 0 at all multiples of pi. And now we're considering 2 pi, 0, and 4 pi, right? So we just get 9 quarters times 2 pi minus 0, which is equal to 9 halves pi. I haven't been shading these boxes today, but that feels good. Any questions?
You said that's a over 2 pi, right? Not 9.
9.
Oh, it is 9. Okay.
There's no 8.
That's why I was confused. Thank you.
Yeah. Okay, Final example of the day. So first off, what if we have the area between two polar curves? So suppose we have r is equal to f of theta and r is equal to g of theta. And suppose that f is greater than or equal to g is greater than or equal to 0. So if I were to draw the graph, here I have my, let's say, f, and here I have my, say, g. Then if I were doing an angle approximate, if I were doing this approximation in terms of wedges, let's say I sample at this point. Let's say I sample at this point. Then I have the area of the bigger wedge minus the area of the smaller wedge, right? So I would have that delta a sub I is equal to pi. Sorry, so it's half. No pi. It's just half of f squared theta. In my notation, it will be s sub I minus g squared s sub I times delta theta I, right? So this is if we're subtracting a smaller wedge from the inside. And so the area becomes the integral of from a to b of 1/2 f squared theta minus g squared theta d theta. Does everyone follow what I did there? So I said, what if we're subtracting a smaller wedge? Well, then we just subtract it from each one of the additional area pieces. And so that gives us this equation. So suppose I consider the following example. Find the area of the region that lies inside of the circle r equals 1, and outside, and this curve is called cardioid. You'll see why. I'll put this in quotes since this is a new term that I'm introducing. R equals 1 minus cosine theta. So if the curve is called a cardioid, then what should its graph look like, just based on that name alone? What does this name suggest?
Maybe a heart shape.
Exactly. So cardio means heart. And if we look at what this is, it's similar to the one that we had before. Here we had 2 plus cosine theta. Here we have 1 minus cosine theta. At the angle 0, so here is the circle r equals 1. Let's draw that circle right here. So this is the circle r equals 1. Then we can consider the circle r equals 2. And so what the cardioid looks like is that at theta equals 0, the cosine theta minus cosine theta is -1. So we have a radius of 0. Then at angle pi, cosine theta is equal to -1. So we have a radius of 1. And then halfway between, we have a radius of 1. And what we get then is a heart shape. Okay, well, in this case, I think I've made the outer radius too big, and so the bulge of the center of the heart. And anatomical hearts, of course, don't look like this, but anyway, it's a heart shape. Now, where do they intersect? So you can do this algebraically. They intersect when 1 minus cosine theta is equal to 1. So that's when cosine theta is equal to 0. And this happens, so if we were going to parameterize this range of angles, what would be the most natural way to parameterize this range of angles right here? Theta ranging from what to what? Well, what's this top angle? What's the upper angle?
Pi/2.
Yep. And what's the lower angle?
Is it 3 pi/2? Or-
The problem
Okay.
is that pi/2 to 3 pi/2 parameterizes this arc right here, right? So if we start counting upwards from pi/2, we get to 3 pi/2. So we should count in the other direction. Then what do we get? What's the lower bound if we count backwards from pi/2? So I can't put 3 pi/2 here because the problem is that this range is not valid, right? So if I subtract 2 pi, go ahead.
So is it negative?
Yeah, minus pi/2. So I should count backwards from pi/2, which is the upper bound. So this is going to be my range of integration. I know that they intersect intersection at pi/2 and minus pi/2. And sort of having some idea of what this looks like. In this case, it's the area that lies inside this circle, but outside of this. So here graphing would probably have actually been helpful. And how would you graph? Well, when you have something like this, you ask yourself, how does the radius change? Well, it's 1 minus cosine. You know how cosine changes, right? You know that cosine ranges from 1 to -1 around the circle. And so what's the radius at 0? Well, it's 1 minus cosine 0. So that's 0. What's the radius of pi? It's 1 minus cosine of pi. That's -1. So 1 minus -1, that's 2, right? And then you draw this shape, and then you figure out where they intersect, and then you figure out the relevant range of angles. So drawing the diagram would have been helpful, but this is the area that we're after. So then if I'm setting up the equation, I have a equals the integral from minus pi to pi. Then what's the first thing that I write?
Wait, it's minus pi and pi because why?
Oh, thanks. Pi over 2. Good. Minus pi over 2 to pi over 2. Yep. Sorry, that was a typo. Now, what's the formula that we worked out? So I should start with the 1/2. What's the outside function?
The circle?
Yep. So that's the function r equals 1. And then I have minus the other function squared. D theta. And so that becomes well, let's write it out. The 1 and the 1 here obviously cancel. Then here I get minus 2 cosine theta, but that becomes a plus. Minus cosine squared theta, d theta. And so I can write that as the integral from minus pi over 2 of cosine theta. And then for the same reason as before, minus 1/4 minus 1/4 cosine of 2 theta. D theta. And I can just write down what the antiderivative is. The antiderivative of cosine is sine theta minus 1/4 theta minus 1/8 sine of 2 theta, ranging from minus pi over 2 to pi over 2. Now, if we look at sine, sine is 0 at pi, multiples of pi, right? So if we look at the sine 2 theta term, it's going to be 0 at both of these end bounds because they were calculating there. The other terms don't vanish though. If I look at the first endpoint, sine of pi over 2 is 1. Then I have minus 1/4 pi over 2, so minus pi over 8. That's the lower bound minus the upper bound. I get minus, so I get sine of minus pi over 2. That's -1. And I have minus 1/4 times minus pi over 2. That's plus pi over 8. And so combining these together, 1 minus -1, that's 2. And this is minus pi over 8 minus pi over 8. So that's minus pi over 4. Yeah, 2 minus pi over 4. And that's the final answer. So these types of polar coordinate problems, sometimes the bounds aren't provided to you, in which case you might actually have to do some polar algebra. But if the bounds are provided to you, then you just set up the integral and you solve it, right? So that's not bad. And it's actually pretty cool that with calculus, we can calculate areas of regions like this. These are pretty esoteric regions, and it's not hard to compute these integrals. At the beginning of the course, you'd be surprised that you'd be able to find a nice expression for the area of something like this. But lo and behold, here we're able to do it. And so that finishes all that I want to say about polar coordinates. We have one topic left in the course, but we should have a break right now. Are there any questions about this calculation though first?
So without the bounds, you were saying we just, how you saying we convert? Or how,
Well,
without
if
the
I
bounds,
give you,
how do we find this?
In this case, you have to geometrically, well, you could solve for this equation, but then you get cos theta equals 0. And then, I mean, that has infinite many solutions. So what are the meaningful solutions? Well, then you actually have to draw a picture and figure out that you're parameterizing this region. So from the picture, you just need to know that this is the region that you're parameterizing. And then you figure out what the angle range is. There are other angle ranges that could work. You could add 2 pi to both of these, right? Angles aren't unique on the circle. You can always add 2 pi. So it's a word problem in the sense that it's not just an integration problem. You also have to set the problem up. And half of the problem is setting up the right integral. So drawing a picture helps in this case. Drawing a picture is always a good place to start. And functions like this, I've explained how I graph them several times. They're not hard to graph. Remember, how would you plot a regular function in high school? You take f at a bunch of values, you put the points, and then you connect a line. Well, here you take r at a bunch of thetas, you put the points, and then you connect the line. Does that answer your question?
Yeah.
Okay, let's take a break until 8:20. And I'll see you then. Okay. Oh, I just realized also that before I had the false impression that this class started at 6:30, it didn't. So I actually spent 40 minutes talking about the exam, which is a bit gratuitous. That was a long admin period. I don't like talking about policy matters for extended periods instead of math. But I think it's appropriate because an oral exam is very unusual. If this were in person, we just have a proctored in-person exam and that would be that, but it's an online course. And I already have a bad indication. And it's also a summer class. This exam would be completely infeasible to run in a 500-person course. In a small class, it is feasible. So those are the differences that we have. In general, multiple people running an oral exam doesn't work either. It has to be one person. Okay. Let's get started. Here. So the next topic is improper integrals. And in general, well, we have FTC2, and if we actually look at what FTC2 says, it's more powerful than what I'm going to assume. But FTC1 applies to functions meeting conditions. Defined on all of a closed interval. Now, for example, the expressions in fact, we also defined actually even better. Let me erase this. Even better. Integration as a whole was only defined for bounded functions on closed intervals. This, of course, means definite integration for bounded functions on AB. So at the moment, we do not even have a notion of what it means to integrate functions on either one of two scenarios. We have no notion at the moment of what it means to integrate an unbounded function unbounded functions again on the range that we're integrating. We're in the world of definite integrals, or of integration for the whole line, the whole or unbounded ranges. So we actually secretly did an improper integral, which we did not do rigorously last time. Technically, you're not allowed to do the integral that we did for computing the length of the circle. That integral was the integral from -r to r of r divided by the square root of r squared minus x squared. This function, the denominator, it blows up at r and -r. So this function is not bounded. And so technically, No, for the fundamental theorem of calculus does not apply. We have an issue. We don't even know we haven't defined what this integral is. We have no notion of integrating this. And then unbounded ranges would be, for example, the integral from -infinity to infinity of 1/1 plus x squared dx. And so what we're going to discuss right now is precisely how to extend integration to those ranges. Giving meaning to this is what we're presently talking about. And so let's do the unbounded ranges case first. Suppose f is integrable on a comma b for all b is greater than or equal to a, e.g. f is continuous. Then the integral from a to infinity of f of x dx is defined to be, so this is a definition. What should it be? Any guesses? Okay, I hope my headphones are connected. I don't think anyone said anything. So we can consider the integral from a to c for numbers c of f of x dx when c is a finite number. And what should we do? We should take a limits as c goes to infinity, right? So what is an infinite integral? It's a limits of finite integrals as the range gets bigger. Any questions about that? Well, then similarly, if f is integrable, I'll just write f is int on, and then I'll write, in this case, I'll write b comma a for all b is less than or equal to a, then the integral from -infinity to a of f of x dx is equal to the limits as c goes to -infinity of the integral, sorry, let's say of b goes to -infinity of the integral from b to a of f of x dx. Now here comes the subtle point. If f is integrable on any, and this is sort of the main point of improper integrals, on any interval a comma b, then the integral from -infinity to infinity of f of x dx. Does anyone have any guesses as to what this should be defined as? You know what, I'll use b here.
would be like 0 to, or
Well, so you're saying a limit, what's the limits? Or is it just one limit? So suppose we make a guess that this should be the limits. So this is a wrong guess. That it should be the limits as b goes to infinity of the integral from negative b to b of f of x dx. Right? So then, for example, if we consider the function f of x equals 0 for absolute value of x is less than 1, and 1 over x for the absolute value of x is greater than or equal to 1. Then if we consider the integral from negative b to b of f of x dx, let's say that b is greater than 1. Then that's equal to the integral from negative b to 1 of 1 over x, sorry, to negative 1, plus the integral from 1 to b of 1 over x dx. And you can see that this integral is equal to negative the logarithm of b, and this integral is positive the logarithm. I should write log. I've been writing log in this course. B, and that's equal to 0. So from the limits as b goes to infinity of the integral from negative b to b of f of x dx is equal to what? What's the limit of this expression?
is it 1?
Well, what's the expression? The expression is 0.
Oh,
So the limit of 0 is as a function of b. Well, it's just 0. 0 doesn't change, right? Every single one of these integrals is 0. So in the limits, this expression is 0. Okay, but now consider instead the limits as b goes to infinity of the integral from negative b to 2b of f of x dx. Then what I get is the integral from negative b to b. Well, I should write the limits as b goes to infinity. And if I look at what I'll get here, I'll get negative log b, negative log absolute value of b. Sorry, this should be, this is the log of absolute value, right? So it's still going to be log b. This is absolute value of negative b, by the way, if you're wondering how I got this. This is for b is bigger than 1. Negative log b plus log 2b. And how can I rewrite that expression? what sort of manipulation can I do here? What is log 2b minus log b?
That isn't log b, right?
Well, I certainly can't take the 2 out of the logarithm. What can I do, though? What's a difference of logarithms? This is the logarithm of what? Assignment 1, question 1.
Can you just combine them? Since you're subtracting one, you would just combine them as, actually, no, it's not B. I'm not sure.
Like, how would you combine them? Well, if you're subtracting, you're on the right track. You would get
Do you divide them?
exactly. So you divide what by what?
Is it 2B divided by B?
Exactly. That is correct.
Okay.
Thanks. And so that's the limit as b goes to infinity of the expression just logarithm of 2. And so what you get is logarithm of 2. So notice that if we basically what we're trying to do is we're trying to sum up the area. And it turns out that if you sum up the area like this, or you sum up like the area like this, you get 2 different answers. And why is that? Why? Because infinity minus infinity can equal anything. And right now what we're doing is subtracting infinity from infinity. Why should the limit be taken like this as opposed to like this? And similarly, why should we divide it at 0? If we divide it at a different point, we're also going to get something different. Well, sorry, I mean, yeah, if we center it around a different point, limits as b goes to infinity of negative b plus k to b plus k of f of x dx is equal to something else. And if you consider this integral, then 0 is in no way privileged among those ranges. Just because 0 is 0 doesn't mean we should center all integrals around it when we expand the range. And what's happening really is that if we consider the graph of 1 over x, so what I've done is I've cut off this graph at 1 and -1. And if I look at this area right here, all of this infinite area right here, well, that's a spoiler alert, but there's an infinite amount of area there. And there's an infinite amount of area there. And the problem with subtracting infinity from infinity is that it can equal anything. So here, infinity minus infinity equals log 2. Here, it's equal to 0. The point is, if you assign a number to this area, it's completely meaningless. These limits say nothing about area. And so the main point about improper integrals is that we want to avoid subtracting from infinity from infinity. So in other words, instead, if we have this integral right here, this is the wrong definition. The correct definition is that we're going to take the limits as b goes to negative infinity of the integral, let's say from b to some point c of f of x dx. And then we're going to separately add the limits as b goes to positive infinity of the integral from c, where c can be any number like 0. to be of f of x dx. And this expression is independent. And in order for this expression to exist, both limits must exist. So we have to evaluate both of these limits independently and see that they both exist for this integral to exist. So I'll write that right here. Both limits must exist. And if we look at this definition in this case, we'd be integrating this area, and we get positive infinity and we get negative infinity. And that's why from this definition, we just see that the limit does not exist. And so we'd say that this integral diverges. If any of the limits, right. So this was a digression. This was to motivate why you can't subtract infinity from infinity. This is a discussion of about the wrong guess. So if there are two sort of singularities, if there are two places in where it's infinite, you have to divide it into two integrals. You have to take the limits separately. By splitting it into two pieces, by splitting it into two limits, we require both limits to exist independently. For the integral to converge. So this is a very subtle point. The discussions thus far has been this. At the beginning of the course, we defined what a definite integral was. That integral was defined for bounded functions on closed intervals. So at the moment, we have no definition at all for what it means to integrate an unbounded function or what it means to integrate over an unbounded range. And so we have to give meaning to these situations. And I'm now discussing this case of unbounded ranges, assuming that the function is integrable on every sub-range that we take. For example, if the function is continuous everywhere, then how we handle just one of the bounds being infinite is we take a limit where that bound goes to the respective infinity. But if both bounds are infinites, then we can't just take a limit as both bounds get bigger, because as we saw in the 1 over x example, that might be meaningless. If you sort of sum it in a different way, if you change how you sum it, you'll get a different answer. And both of these numbers can't represent the area. And the reason that we're getting two different numbers is because we really have a situation where we have infinity minus infinity. And infinity minus infinity can be made equal to any number whatsoever. So by actually changing how you change those bounds, you can make this equal to any number whatsoever. In particular, if you just change it to something b, then you get log of that number. And as b ranges from 0 to infinity, log of that number ranges from negative infinity to infinity. So by putting in just k here, you get log k. So by putting in e to the k here, you get that specific number. So you can literally make this integral equal to anything if you just change how you sum it. And so that's completely meaningless to an area. And that's why we have to make a definition in the two bounded case of writing it as a sum of two limits and requiring both limits to exist in order for the area to be meaningful. Any questions about that? So all of these are definitions of what it means to take these integrals. Okay, I'll give some examples. Examples of computing improper integrals. So this is how you would write up a solution for computing an improper integral. let's say we consider the integral from negative infinity to infinity of 1 over 1 plus x squared dx. Then in order to compute this integral, what we consider first is the limits as b goes to negative infinity of the integral from b to 0 of 1 over 1 plus x squared dx, which is equal to the limits as b goes to negative infinity and what's the antiderivative of 1 over 1 plus x squared?
The arctan.
Yep. Arctan x, and then I evaluate that between the bounds of b and 0. And what I get then is that this is equal to the limits. And notice how I had limit here. And so after every single equality, I have to write limit. If I stopped writing limit, I'd be writing false statements. In fact, I'd be writing meaningless statements because b is meaningless without the limits, as that quantifies to b. So they wouldn't even be false, they'd be nonsensical. So I have to keep writing limit. If I drop it, then I'm writing nonsense. Okay, well, arctan of 0 is 0. And so I'm just looking at limits of 0 minus arctan b, right? And what's the limits of minus arctan b as b goes to negative infinity? What does the graph of arctan look like? Well, first off, we have the graph of tangent, right? Go ahead, if someone was going to say something.
Oh, will the limits be related to its asymptotes?
Yes, they are. So this is the graph of tangent. We reflect it. And what are its asymptotes?
Negative pi over 2 and pi over 2.
Exactly. So as b goes to negative infinity, arctan of b goes to what?
Negative pi over 2.
Exactly, and then it's negative arctan of b, so that goes to pi over 2. So I've found this limits. Then I consider the other limits. Limits as b goes to infinity of the integral from 0 to b of 1 over x squared. Well, okay, 1 plus x squared, I wrote it like that before, dx. And then this is equal to the limits as b goes to infinity. Notice that I keep rewriting the limits, and I want you to do this on the homework. I will get annoyed if you drop the limits. You have to keep writing the limit until you evaluate it, of course. But unless you've made the limit go away, you should keep writing it. Okay, the antiderivative is the same. And then the bounds are 0 to b. So this is the limit as b goes to infinity of arctan of b. I guess minus 0. And that's equal to what? Someone else.
Pi over 2.
Good. And so therefore, I can write therefore, by definition, the limits from negative infinity to infinity of 1 over 1 plus x squared dx is equal to pi over 2 plus pi over 2 is equal to pi. And that completes the answer. And it was absolutely essential that I split it up into two limits and I calculated both limits independently. Because we saw before, it's examples in which we could have infinity minus infinity, and then you could get any number whatsoever depending on how you took the limit. So we want to weed out those situations. And because we want to weed out those situations, what we have is we have to split it into two integrals.
Can you explain where you got the pi over 2 from real quick?
Yeah, sure. So I have the function tangents. And if I look at the graph of tangents, it has asymptotes at pi over 2 and minus pi over 2, right? Now, what does the graph of arctan look like? It's the inverse function of tangent. How do I get an inverse function? Well, first off, I take a specific range over which the y values have their biggest range. So the y values range from negative infinity to infinity. So I restrict the range to here. All inverse trig functions have a specified range that they come with. For tangent, it's this range. And then I take the graph and I reflect it across the 45-degree line. So these vertical asymptotes become horizontal asymptotes. And those are where the asymptotes are located. And so what am I doing? I'm taking the function and I'm looking at evaluate its values as those values go to infinity. And what does the function approach? The function approaches the value of its asymptote, right?
Yeah.
So the limits as b goes to negative infinity of arctan of negative b is minus the asymptote minus pi over 2, which is pi over 2.
Okay, so it's because of the graph.
Exactly. So you have to know what the graph of arctan looks like. You are, so this is a function that you should keep in mind. It's part of your toolbox. You need to know stuff about it. Let's do another example. Let's consider the integral from 1 to infinity of 1 over x dx. So this is equal to, let's divide this. The limits as b goes to infinity of the integral from 1 to b of 1 over x dx. And I have an antiderivative for that. So by the way, because only one of the bounds is infinite and because the function is bounded and well behaved on every other range that I consider, because we're not considering, it blows up at 0, but we're away from 0 because we're looking at 1 to b, b is bigger than 1. In the limits, b avoids, this range does not contain any asymptotes. So we don't have to split it up into two integrals, so I'm not evaluating two limits separately. It's just a single limits, and then I write that down. And so I know what the antiderivative is. It's the logarithm of, and then I can write absolute value, but both of these values are positive, so I may as well just write logarithm of x from 1 to b. Or I can write absolute value and then it'll go away in a second. Well, that's equal to the limits as b goes to infinity. B is eventually bigger than 0. It's eventually bigger than 1. So I get the limits of logarithm of b minus 0. And what's the limits as of logarithm as its argument goes to infinity? Is logarithm bounded? What does logarithm happens for logarithm for large values?
Is it going to 1?
So you're saying that if I take the logarithm of 1 billion, it's close to 1?
No.
If I take the logarithm of 1 billion, what's that going to?
Infinity?
Yeah. So i.e., this integral diverges. Infinity is not a number, so we say this integral diverges. Okay, let's in general, here's a good example. Consider what happens if p is a number. Let's say p does not equal to 1. And we're going to consider the integral from 1 to infinity of 1 over x to the p dx. So the case p equals 1 was handled here. In this case, it's the limits as b goes to infinity of the integral from 1 to b of 1 over x to the p dx. And what's the antiderivative of this if p does not equal to 1? Oh, I will give you a hint. We can write this as the limit as b goes to infinity of 1 to b of x to the minus p, right? So what's the antiderivative? We just use power rule. What do I get?
Is it x to the minus p plus p all over p?
Plus minus p plus what? What's the exponent?
P? Or
1.
Yeah, we add 1, right? And then what do I have to divide by?
Negative p plus 1.
Yeah, exactly. And so that's the antiderivative, and I'm evaluating that between 1 and b. So that's equal to the limits as b goes to infinity of, well, 1 over, I'll write this as 1 minus p more elegantly, and then I can consider b to the minus p plus 1 minus, and then if I put 1 here, I just get 1 to some power, which is 1. Now, if I take b and I raise it to some power and I let b go to infinity, then what happens? And it depends on what the power is, right? So tell me what happens. So if p plus 1 is less than 0, then what?
Would the number become infinitely small?
Yes. Then we're dividing, then we have limits of 1 over b to the, let's say, c for c greater than 0. And that's equal to 0. So limits of b to the minus p plus 1 is 1 divided by an infinitely large number, which is an infinitely small number, so that goes to 0. On the other hand, if minus p plus 1 is greater than 0, and we have no case in between because we assume that p was not equal to 1, we get the logarithm otherwise. Then what? We're raising b to some positive power, right? So in the limits,
It's gonna get bigger.
yeah, unboundedly big. So IE does not exist. In other words, then going back here, the integral from 1, you know what, I'm going to do the trick that I had before. I'll write a star. So I'll write if if P is bigger than 1, then star is equal to limits. Well, I can look at this -1 and I can write that as 1 over P minus 1. So changing the order to account for the negative sign. And then I can write 1 minus the limits as b goes to infinity of b to the minus p plus 1. And that's equal to 1 over p minus 1, 1 plus 0. So that's equal to 1 over p minus 1. And then if p is less than 1, on the other hand, then star equals to the limits, the same limit as before. Sorry, yeah. Okay, I can write it also as limits 1 over p minus 1, 1 minus the limits as b goes to infinity of b to the minus p plus 1. And this we found does not exist. If p is less than 1, then p minus 1 is negative. I mean, it goes to positive infinity, but anyway, it does not exist. And so this is actually a result, and you can cite this result. This is called the p-test. And that says that the integral from 1 to infinity of 1 over x to the p dx is equal to, and then we can do divide cases. If p is greater than 1, then it's equal to 1 over p minus 1, and does not exist otherwise. And this is a named results. And we're going to see that it's actually useful. So this is a very important thing to know. When is this area infinite and when is this area finite? If p is greater than 1, if you're dividing by something that's not just the power of p, but it's like 1 dividing by x to the 1 plus epsilon, for epsilon positive, then the area becomes finite. Otherwise, the area is infinite. So this answers the question of when, if I look at it like this and I draw 1 here, and let's say this function is 1 over x to the p, of when this area, the shaded area, is positive. Sorry, when the shaded area is finite. And we consider this a pretty important result. In calculus C in particular, you will have lots of comparison tests for determining whether series converge. And the integral comparison test will compare the series to an integral. And then whether the integral converges or not will tell you whether the series converges or not. And often those integrals can be compared to integrals of this form. And so this is a very important integral for Calc C. This is in Calc C, you will use this a lot. But it's part of the Calc B material. Any questions about that? By the way, let me just quickly show you something. I wanted to show you this. One second. So here is the course homepage for Mat 126, and here is the description, the usual syllabus of what's in Calc B material. So you'll see just the definition of the integral, the fundamental theorem of calculus, substitution and integration by parts, trigonometric integrals, partial fractions, improper integrals, areas and volumes, arc length, and applications. I consider areas and volumes to be applications. I consider myself to have done applications. Some people like to do word problems with more words, but you can see that what we've done, maybe the first week was not ideal in terms of the definition of the integral, but then afterwards, we've just basically stuck to this, and that's the course material. I have a few more things to say about improper integrals. I need to also say what happens if the function is unbounded, right? But otherwise, after we do that, we'll have finished the course material exactly as it's given as to what this course should consist of, right? Everyone agree?
Yep.
So what I covered is exactly the standard material. Okay. And then we do this in calculus B because it fits into this discussion of improper integrals, and in calculus C, you'll do this law for series. Okay. Now I will discuss the next case, which is unbounded functions. So suppose we're going to assume f is integrable on every closed subinterval. Of the relevant domains. So those assumptions mean different things, and then I'm going to write a table. Suppose that f is bounded on, if f is bounded on then and then I'll divide this into cases. So if f is bounded on the interval a to b, open a to b, so the problem is that the endpoint a is missing, then the integral from a to b of f of x dx should equal what? What limit are we going to take? Which endpoint is going to which endpoint? What endpoint stays fixed?
Would it be infinity to b?
Well, it's not infinity. We're trying to make, so the function is integrable on every interval between a and b, but the problem is that the function is unbounded at b. So it's not infinity, it's something that's going to the endpoint, which well, let's say C. And what is C going to? Well, it's pretty clearly going to be A, and there's one more catch. The integral isn't defined when C is less than A because the function might not be bounded at A. So we're actually taking a one-sided limit. And since we're taking this limit from values that are just bigger than it, then it's a one-sided limit and we write it like this. So this is for C just bigger than A. It's approaching from values that are slightly bigger than A. So this is a one-sided limit if you remember from calculus A. This just means that values C less than A do not factor into this. Well, it's this integral of f of x dx. Now, correspondingly, if it's bounded on A to B, with B being omitted, well, then it's equal to the limits as C goes to B from the lefts of the integral from A to C of f of x dx. So all of these are definitions, by the way. Now, what if it's just bounded on the open interval A to B? What should I do? What do I need to do? For the same reason as before.
Are you splitting it up into two intervals?
Exactly. So let's say D be between A and B. Then the integral from A to B of f of x dx is defined to be the limits as C goes to A from the right of C to D of f of x dx plus the limits as C goes to B from the left of D to C of f of x dx. So what's the main lesson? The main lesson is that if there's only one place in which it's unbounded, you just take a one-sided limit. If there are two places, then you take a two-sided limit. However, there's one more case, and this case comes up very frequently. What if it's bounded on the interval, closed interval A to B, less a point in the middle? So for example, 1 over x blows up at 0. And sorry, it's bounded on any closed subinterval of. It doesn't have to be bounded on the entire range, on any closed subinterval. So the examples that I mean, for example, in this case, 1 over x. If I look away from 0, if I take any closed interval that does not contain 0, then the function 1 over x is bounded. But it's not bounded on all of A or B. The point is that if I consider these limiting expressions, all of them are defined. But it's not defined if we just consider it otherwise. Anyway, in this case, if there's a point at which it blows up, then what should I also do? Should I also split it up into two integrals? Well, I should. So I can take the limits as C goes to, in this case, the point D. And let's say I'm going to take it from the left of the integral from A to C of f of x dx. And then I can add to this the limits as C goes to D, from the right of the integral of C to B of f of x dx. So if I consider, for example, trying to integrate 1 over x, spoiler alert, there's going to be an infinite amount of area. around the point at which it blows up, then you can see that it's possible for there to be minus infinity plus infinity, right? There's room for this area to be infinite and for this area to be infinite. And I don't want those two areas to cancel each other out, so I have to split it up into two integrals and take both limits individually. And what this means in practice is that you're going to have something like you had before. If I wanted to compute this integral, I'm not allowed to just find the interval on some specific range and take the limits. I have to split it up into two integrals, and I have to take those two limits separately. And that's really the main point of improper integrals. You're taking the limits, and if there are two places at which things go big in either the range sense or in the unbounded sense, then you have to split it up into two limits and calculate them separately. So what time is it now? I have 5 minutes left. So I will do one example then. Are there any questions about this, by the way, first? I will actually admit that all of this material is a bit tedious. You just have to write the problems up in a specific way, where you split it into two pieces in the case of two unbounded things and take a limits. And asymptotes come in. You need to know things about asymptotes of functions, for example, here, right? So you actually need to evaluate some limits. So here we have limits and integrals combining. So let's do example. The integral from -1 to 1 of 1 over x dx. So what we're going to do is we're going to consider the limits as, let's say b goes to 0 from the left of the integral from -1 to b of 1 over x dx. It's important that it's a one-sided limit because for positive values of b, this expression wouldn't be defined. It would be defined recursively in terms of a limit. And so what's the antiderivative of 1 over x? It's logarithm of the absolute value of x. And that ranges from -1 to b. And you can see that's the when we plug in 1, we get 0. When -1, we get the absolute value, so we get logarithm of 1 is 0. And then if we look at the upper bound b, we just get logarithm of the absolute value of b. And as b goes to 0, this goes to logarithm of b goes to -infinity, because if we look at what the logarithm is, what's the graph of the logarithm, right? It looks like this. And the argument, absolute b, it's going to 0, right? And as x goes to 0, this goes to -infinity. This limit does not exist. And we don't even have to evaluate the other one because both limits have to exist for the function to exist. Therefore, the limits as, not the limits, therefore the integral from -1 to 1 of 1 over x dx diverges. And then I have one more example and some material about comparison tests, which I'll do on Friday. And then the rest of the lecture is going to be a review lecture, except for the fact that at the end, I'll do 45 minutes of fun material and talk about complex numbers, although that's not part of the official course material. So most of the lecture is going to be review. There's going to be a bit about comparison tests, which are just going to be relevant for the last homework. But other than that, we basically almost finished the course material. So I'm going to wrap up the material and then I'm going to do the review lecture on Thursday. And then a bit of fun stuff at the end. Sounds good?
Yep.
Right. And then if anyone joined in late, remember that we are going to have an oral exam next week. It's going to be on Wednesday and Thursday. And then I'll send up signups for time tomorrow, as well as some more details. Okay, that sounds good. So I will see you on Thursday. Expect an email from me tomorrow.
Is the sign up going to be sent via email, or will it be on?
It is.
Okay.
So I haven't been using like posting things to Blackboard ever. The other
Right,
option
right,
will be on the
right.
course website, but I send people emails. It's going to be a Google Doc, and then there are going to be slots.
Thanks.
Any other questions? Nope. Okay. Well, see you on Thursday.
Thank you.
No worries.
Have a good night.
Likewise.